Welcome to the part 2 of making a 2-channel boombox. Well, from the previous video, I got some feedback, out of which one was pretty much expected, to make the video shorter. And that properly makes sense because hey, during exams, the smallest chapter was always the most interesting. And others were making the proper lighting conditions or making the background noise disappear. Well, in this video, I'll be testing the UTC2050 circuit board. So without wasting any further more time, let us move on to the circuit of it. Now generally, the circuit boards will come like this, where all the components will be marked, and I have drawn this circuit accordingly with all the components marked. Now what is happening is, the small signal is coming from here and it is getting amplified as the large signal, and whatever components which are relevant to the small signal should be connected to the small signal ground, and whatever components which are relevant to the large signal will be connected to the large signal ground, or basically the power ground. And now let us move on to the circuit explanation of how this circuit works. Now if you want to take the screenshot of the circuit, you can go ahead and take the screenshot. This circuit is not very much different from what is already present in the data sheet. Now these boards are compatible with LM1875, UTC2050, UTC2030, TDA2030, TDA2030A and all other 5-pin ICs, because they almost have the same pin out and same list of passive components. So we'll go ahead and look at the calculations. Now first comes is the gain of the amplifier. It is very important. Say AV is 1 plus R4 here and R6. I would say anything beyond 30 is not good. It will lead to a lot of noises and distortions and it will be very hard to fix those. So keep it below 30, it will be a good gain design. Now let us move on to the next thing, that is this part of the circuit, which is very important. Now if you look at the first portion of it, the C13 and R2, now this C13, which is 2.2 microfarads, this is usually used to block the DC that is present in the input signal. So the DC, if it's not properly cut off, it will get amplified through the amplifier and it will create a big DC offset. DC offset can also be measured with a multimeter in the output of the amp, and DC offset, the lower the DC offset, the better the amp is. So if you see at C13 together with R2, this basically makes one high pass filter. The main purpose of this high pass filter is to block anything below 2 Hz. And the equation is fairly simple to calculate these two values. It's again FC is 1 by 2 pi RC. Next comes is this part of the circuit, R1 and C6. If you look at this part of the circuit, R1, which is 5K, and C6, which is 100 PF, this usually makes a representation of a low pass filter. So high pass filter, we have a cutoff at 2 Hz, and low pass filter, we have a cutoff at say 250 to 300 kilohertz. So this part of the circuit is to prevent any radio frequencies that are incoming, and that can also lead to a hiss sound in the output of the amplifier. There is another very much important calculation that I'm going to do, which is also one tip for designing this type of amps. So if you look at this resistor R1 and this resistor R2, and if I just draw roughly here, say this is R1 and this is R2, and we'll take this R4, which is also the feedback network. This is the inverting, this is the non-inverting lead. Now this R4 should be equal to the addition of R1 and R2, or at least very much close to R1 and R2, because if it's not very much close, it will create a difference of current in the input of the amp, and if it creates that difference, it will also lead to a DC difference in it, which will get amplified and which will lead to a DC offset again in the output of the amplifier. So this is important, and that's why I have kept this as 5k, 15k, and this is 20k, which is equal, and we'll use metal thin resistors which will make the value very much close. Now once this is done, we are only left with one calculation, that is the Zobel network. So the Zobel network, if I draw it roughly here, comprises of the resistance R5, 2.2 ohm, and the capacitor C10, that is 0.22 microfarads. Now the main reason to keep the Zobel network is to prevent the oscillations coming from an inductive load, which is nothing but our speaker also. And one more thing is that, see, the signal ground is this one. I'll highlight it with the blue pen. So signal ground is this one. So all the connections which are relevant to the small signal is this, the input signal, are only connected to the signal ground or the audio in ground, and connections which are relevant to the large signal, which is the output of the amp, suppose this one, I have marked it with this, the ground symbol, are all connected to the main power ground, and this input signal ground is connected to the power ground with a 10 ohm resistance. This will eliminate any indifference being created with the ground loop, or voltage indifference being created in the ground loop. So that's it with the circuit calculation. We'll directly move on to testing now. So let us start the testing. As you can see, I've made all the connections in here. Let me quickly go through the connections. So this is where the AC input is coming in to the toroidal transformer. Well, by the way, this toroidal transformer is from Galaxy Transformers. They are really professional people, and you just give them your voltage and current requirement and the wattage of the transformer you want. They will wind it and deliver to you in no time. So the AC input is coming from these two green wires, and I have connected this bulb limiter in series with the line. If you want to know more about how this bulb limiter works, then you can see the YouTube shorts that I've uploaded recently, and you can maybe find the video somewhere in here. So the AC is coming in, it is getting stepped down by the transformer. One of the windings is 12 volts, and 12 volts is getting rectified, regulated to 5 volts, and this is the power for the Bluetooth module. Then again there is this 12 winding center tapped, which is getting regulated and filtered for the preamp board. So we are getting 12 plus minus DC 12 volts for the preamp. So Bluetooth is getting 5 volts, Bluetooth output is connected to the input of the preamp, preamp output is connected to the input of the amp, and this is another winding 13013, which is getting rectified and filtered, and we are getting close to 18 volts in here, which is the input to the power input basically to the amp here. This is plus, minus and 0 ground. So we are getting DC plus minus 18 volts here for the amp, and we have here our output of the amp connected to the woofer. So that is all the connections in here. One more thing which I want to add is, see this ground in here, this is the main power ground for the this is the main power ground, which is basically also the main center tap supply for the amp. This is one power ground, and this is where the signal ground is, basically this where. So this ground and this ground, they are isolated galvanically, and these two are separate windings inside the transformer, so they are nowhere connected in here. Only place they are connected is basically through this 10 ohm resistance, which I've explained earlier. And now I did not test it before, so if I just power it on, the bulb should glow and stop glowing. It should glow for a second and then stop glowing, because obviously it will take a lot of current to charge the capacitor, and for that it should glow for a second and then it will stop glowing. That means everything is fine. If it continues to glow, something is wrong. Magic smoke might come out. I don't know what will happen, but let us find out.
Bluetooth mode.
Just joking. So nothing happened and everything is fine now. I'll remove the connection for the bulb here. So I've connected it with the Bluetooth, and let me play some YouTube safe music. So let us start. You can see there is almost zero noise in this. So if you lay out properly, if you lay out your amp properly, there will be almost zero noise. So now let us move to testing it with our function generator, and let us see how much power, RMS power, it can produce. So I've connected everything for testing. This is our function generator here, which will be outputting 1 kilohertz, and this output of this function generator is going to get fed to the amp here, and this is the same supply, same toroidal transformer, and this is outputting close to 18 volts plus minus DC, and the output of the amp is connected to this 8 ohms 100 watt resistor, and I have connected this oscilloscope across the resistor. And now if I just switch it on, so if I increase the amplitude of the sine wave slowly, you can see the wave, the output of the amplifier in the oscilloscope. So our target is to go to a point where it starts clipping from the top and the bottom. Really, clipping means the amplifier is not amplifying anymore, in simple words. So let me increase it slowly. So if I just increase the time base here, this is horizontal channel 1, horizontal channel. Yes. So now our target is to see clipping, and if we see, yes, you see this straight lines in the top and bottom, this means clipping, and this is where the amplifier stops amplifying it and starts introducing DC component in the output. So we'll just reduce it to the point where it just starts clipping, and yeah, we will take it as 31.2. I'll just make the video, yeah, 31.6. Now just for information, this is the input voltage that I'm feeding, input signal basically that I'm feeding. So it's 1 kilohertz and it's 1.7 volts peak to peak. Now we'll go into the calculation and see how much wattage it's actually producing. So our V peak to peak was 31.6 volts, and we know V RMS is nothing but 31.6 divided by 2 root 2, which is equivalent to 31.6 divided by 2.828. This gives us something, this gives us 31.6 divided by 2.828, it's 11.17, and PRMS is basically VRMS square divided by resistance, and PRMS then is equals to 11.17 square divided by 8.3 ohms. So this gives us 11.17 into 11.17. This is 124.768 divided by 8.3. That is exactly 15 watts. Now I am pretty surprised to see that it actually delivers this wattage, and whatever we calculated in the first video, it's very much similar to the calculations now. I'm very much curious to see what LM1875 will do in this place. So in the next video, what I will do is I will solder LM1875 in this place, in the place of UTC2050, and in the same condition we will see how much wattage LM1875 produces, and also we'll test it with 4 ohm load in place of 8 ohms. So I'll link the Galaxy Transformers WhatsApp contact in the description, and I'll also link Vipin's number from whom you can get authentic LM1875 ICs and also this circuit boards. So that's it for this video. Thanks for watching. Please like, share and subscribe. I'll see you in the next video. Bye.